Hey everyone, welcome back. Ready for another deep dive?
Always.
Awesome. So today we're tackling radiomics.
Specifically, how AI is being used to analyze medical images. It's like, boosting doctors' X-ray vision for diagnosis and treatment.
Right, and I know Lecture 6 in our BE 645 course got, well, a bit complicated. So this is kind of like your cheat sheet for those, trickier concepts.
Yeah, it's really incredible. We're basically teaching computers to see patterns in these images, just like a radiologist would. But the amazing thing is AI can do it so much faster and with incredible precision.
Okay, so let's break down this process. First up, the radiomics workflow. It's like a step-by-step recipe. 6 key ingredients, each powered by AI in some way.
That's a great analogy. It all starts with acquisition and segmentation. So you get the images like CT scans or MRIs, and then you focus on the region of interest, the ROI.
Okay, so like highlighting the important part of the image. And this segmentation, it can be done manually, right?
Yeah.
Like a radiologist outlining the area.
Yeah, that's the traditional way. But this is where AI comes in automatic segmentation. It saves a ton of time, and it also makes the process more consistent, less room for human error.
So getting rid of those little inconsistencies, that can make a big difference, right?
Absolutely. So then we move to feature extraction. This is basically translating the image into something AI can understand. We use algorithms to measure things like shape, size, texture, even how bright different parts are.
So we're turning the image into a set of numbers, basically.
Exactly. And then comes pre-processing. Imagine you have this mountain of data. You got to filter it and find the important stuff. Pre-processing helps us select the most relevant features, so the AI focuses on what matters.
Makes sense, like getting rid of the noise so we get a clear signal.
Right, and you'd think more data is always better, but too much irrelevant data can confuse the AI. Pre-processing is like quality control for the data. So once we have that nice, refined data, then we get to the core of it all, AI model development.
The brains of the operation. Tell me more.
This is where we design the AI algorithm, often using these things called neural networks. They're complex algorithms, kind of inspired by the human brain, that can learn from data and make predictions, like, teaching a dog a new trick.
So we're training the AI to become an expert, like we train radiologists to spot those subtle signs of disease. And this training happens during model training and evaluation, right?
Exactly. We feed it tons of data so it can learn patterns. But we also need to validate and test it, make sure it works on data it hasn't seen before, not just the stuff we used to train it.
So making sure it can pass any test, not just the practice ones. Then we have explainability. The AI has to be able to show its work, not just give us an answer.
Right, especially in medicine where those decisions have real consequences. Understanding how the AI got to its conclusion, that's super important.
So now let's dig into the different levels of feature extraction. This is the part that got a bit confusing, I think, in the lecture. What exactly are first-order features?
Well, they're like the most basic features taken directly from the histogram, like a graph, of the pixel intensities within the ROI. It's analyzing how bright or dark different parts are.
So it's like a basic overview of the image, the overall brightness and contrast.
Yeah, exactly. But we need more detail. That's where second-order features come in. These analyze how pixels relate to each other, not just their individual intensities.
Okay, so instead of looking at each pixel alone, we're looking at how they connect.
Yeah, they use matrices like the Gray-Level Co-occurrence Matrix, GLCM, to reveal those textures and patterns. And then we have higher-order features. They use even more complex math to capture really intricate patterns, going even deeper into texture and shape and all that.
It's like adding those finer details to a drawing to make it more realistic.
That's a great way to think about it. Now let's focus on a specific second-order feature, the Gray-Level Size Zone Matrix, or GLSZM. This one's really important in medical imaging.
Okay, here's where things get interesting. So GLSCM focuses on zones in the image. Can you explain what a zone is?
Sure, a zone is basically a group of connected pixels that all have the same intensity value, the same shade of gray. The GLSCM looks at the size distribution of these zones.
So like if we group together pixels of the same shade, how many are in each group? That tells us how uniform or, well, how varied the texture is.
Exactly, and that's important because it can help us analyze things like tissue heterogeneity, how much variation there is in the tissue. That can be a sign of disease, like a tumor might have a more complex texture than healthy tissue.
So by analyzing the GLSCM, we're getting a kind of fingerprint of the tissue texture, which can help us with diagnosis, and even predicting how a disease might behave.
Okay.
This is amazing. Now, how do we actually calculate this GLSEM? There are these parameters involved, right?
Yes, there are three key parameters: number of gray levels,
All right.
maximum zone size, Ns, and connectivity. N is simply the number of different shades of gray in the image.
Okay, so if we have 256 shades of gray, then N is 256. Got it. What about maximum zone size?
Ns is the largest zone size we'll consider. Theoretically, it's calculated by multiplying the image dimensions.
So for a 2D image, it's width times height. For a 3D image, it's width times height times depth. Like we're setting the upper limit of how big a zone can be, right?
Makes sense.
And finally, there's connectivity, which sounds kind of tricky. Can you explain that a bit more?
So connectivity tells us how we decide whether pixels are connected. In 2D images, we usually use 4 connectivity pixels are connected if they're next to each other horizontally or vertically, or 8 connectivity, where we also count diagonal connections.
Does it really make a difference which one we choose?
It can, yeah. It's subtle, but important. Imagine you have a checkerboard pattern. If you use 4 connectivity, each square is a separate zone. But with 8 connectivity, the whole board could be seen as one big zone.
Ah, I see. So the choice depends on the type of texture and what we're looking for. Fascinating. Now, I know we're going to dive into the actual GLSEM calculation, but first, can you give us like a general overview?
Sure. Imagine the algorithm as a detective searching the image for clues. It follows the trails of connected pixels to map out the zones and their sizes. That way we capture the full texture of the image.
It's like the algorithm is putting together a puzzle to reveal the hidden patterns.
Hmm.
I'm ready to see this detective in action. Let's move on to the calculation. Okay, so let's get into the nitty-gritty, the actual calculations for the gray-level size zone matrix. I'm ready to see how this all works.
All right, time for our detective to shine. We talked about those parameters in part 1, number of gray levels and maximum zone size and connectivity. And see now, let's see how we use them to create this matrix.
I remember seeing the matrix in the lecture and thinking, how do they even calculate that?
It's actually not that bad once you break it down. Remember that simplified example we talked about, the 5x5 matrix with values from 0 to 3?
Right, our mini image. Each cell has a value, 0, 1, 2, or 3, showing its intensity.
Exactly. And we said we'd use 8 connectivity, right? So we're looking at neighbors in all directions. First, we create an empty matrix. This will become our GLSZM. It'll have N rows for the gray levels and N's columns for the maximum zone size.
So in our example, ideally it would be a 4 by 25 matrix, 4 gray levels, and the maximum zone size is 5 times 5, which is 25.
Right. But for simplicity, we'll stick with 10 columns, just like in the lecture. So a 4 by 10 matrix, all zeros at the start.
Okay, I can picture that, an empty matrix waiting for us to fill it in. How do we actually do that?
This is where the algorithm steps in. We go through the image pixel by pixel, and for each one, we check if it's part of a zone. If it is, we figure out how big that zone is and update the corresponding entry in our GLSCM.
Hold on. Let's say we pick a pixel, and it has a gray level of 2. How do we know what zone it belongs to?
We check its neighbors. Remember, 8 connectivity, so we're looking up, down, left, right, and diagonally. If a neighbor also have a value of 2, then it's part of the same zone.
It's like a chain reaction, spreading out from our starting pixel. We keep going until we've mapped the whole zone. What happens then?
Well, once we know all the connected pixels with a value of 2, we know the size of the zone, right? Let's say it has 5 pixels. So we go to the row for gray level 2 in our GLSZM and the column for size 5, and we add 1 to that entry.
So each entry in the matrix is like a counter, keeping track of how many zones of that size there are for each gray level.
Precisely. And we do this for every single pixel in the image. Our detective goes through meticulously, examining each one, finding its zone, and updating the matrix.
This algorithm is doing a lot of work.
It is, and this is where recursion comes in. It allows the algorithm to efficiently explore the image. It follows all those branching paths of connected pixels without getting lost or counting anything twice.
So it's not just about counting pixels, it's about seeing how they're connected and how that creates the texture. So once we have this GLSEM filled in, then we can calculate all those features, like small zone emphasis and large zone emphasis and gray level non-uniformity.
Exactly. The GLSZM is the basis for all those texture features. It connects the raw pixel data to those more meaningful characteristics that we can use for diagnosis, treatment planning, and all sorts of things.
It's amazing how we go from pixels to zones to a matrix, and finally to these texture features.
It is remarkable. And remember, this was a very simplified example. In real applications, we're working with much larger images, sometimes 3D, and the calculations get more complex. but the principles are the same.
I'm excited to see how this all comes together in practice. In part 3, we'll talk about those Python scripts you mentioned, the ones that can actually calculate the GLSCM and its features.
Yeah, it'll be interesting to see how this seemingly abstract matrix can help us make a real difference in healthcare.
Welcome back to our deep dive, everyone. We've spent the last 2 parts exploring the gray-level size zone matrix, going from pixels to zones to this matrix, and how it can be used to quantify texture features. It's been quite a journey.
It has. And now we get to see how this all translates into something practical. Remember those Python scripts I mentioned? The ones that can actually calculate the GLSZM and its features.
Yeah, those sounded really interesting, especially for our student listeners out there. Getting hands-on experience is so valuable.
Definitely. And these scripts are designed to be pretty user-friendly. You can find them on GitHub in a repository specifically for the BE645 course. We'll put the link in the show notes.
Perfect. So even if we're just getting started with Python, we can still use them?
Oh, absolutely. There are separate scripts for 2D and 3D images, and they not only calculate the GLSCM, but also extract all those features we talked about, like small zone emphasis and large zone emphasis.
So you give it an image, define the segmentation mask, and it gives you all these texture features ready to be analyzed. That's pretty cool.
Yeah, it makes things much easier. And then the exciting part is using those features for all sorts of applications in medical imaging. You can feed them into machine learning models to help diagnose diseases, predict how patients might respond to treatment, even personalize treatment plans.
So it's not just about quantifying texture, it's about actually using that information to improve healthcare, to make a difference for patients.
Exactly. And it really shows how powerful computational analysis can be when applied to medical imaging. And it brings us to a final thought I'd like to leave you with. We talked about how the choice of connectivity, like 4 versus 8 or 6 versus 26, can influence those GLSCM calculations. So think about this. How might that choice affect those final features, those texture features, and how we interpret the image? Could lead to different insights, maybe even different diagnoses or prognoses. It's something to consider.
That's a great point. Even in this world of, objective computational analysis, we still have choices to make, and those choices can have real consequences. It reminds us to be critical, to always question our assumptions.
Absolutely. And that wraps up our deep dive into radiomics and specifically the gray-level size zone matrix. I encourage you to keep exploring this field, play around with those Python scripts, and keep thinking about the potential of these techniques.
Thanks for joining us, everyone. And until next time, keep learning, keep questioning, and keep exploring.